Welcome to installment 17 of writing a 6502 assembler in assembly language. In the last episode, we went back and tried to test the symbol table code to make sure that it worked, and it seemed to sort of work, mostly work. There's just a few things I have to take care of to check and make absolutely certain that it works. First off, as I noticed that last time, some of the things that should be keywords, such as .bss, were not being treated as keywords. They were being treated as symbols. So I want to figure out what's going on there. Also, there was this special symbol called dot, and that one needs to be handled specially. So I would like to make sure that that is handled specially and is not handled as a symbol. It comes back as a keyword. It should come back as a keyword. And then I had the idea that just to make sure everything's going well and everything's working properly, I would like to write some code to dump out the entire symbol table so I can see the status of it at every time throughout the reading of the input so that I can make sure that everything is working correctly. And so let's look in that stuff. And first off, we'll go back into our file AS1, and here are these keywords. So all of the pseudo ops are up here, and there are 12 of them, and they start with a dot. And here they are in the keyword table, which is actually binary search to find keywords. Now, if it's found, like for example, if we were to find BSS, that is the fifth string here, the fifth thing. There it is right here, okay? This is the pointer to .bss. Then it would return whatever it comes down here as the token, whatever is down here in the same position, okay? So this is 0, 1, 2, 3, 4, as we see there. So this would be 0, 1, 2, 3. It would return TPSC plus 4. And TPSC is, if I remember correctly, 128. Basically, it means token pseudo-op. So the pseudo-ops are just returned as TPSC plus 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And after that, we return different values that are related to the instructions. So this would be the token type that's returned would be TPSC plus 4. And then the token value return comes out of this one. And for the opcodes, this is for the instructions, this is just a representative opcode for the instruction. For the pseudo ops, it just returns 0. And that, I think, is what's going on here, because in the is keyword subroutine, if it finds that something is a keyword, it returns this value in A, and it returns this value in Y. So the value from the keytoke table is returned in A, and the value from the keyval table is returned in Y. And I will jump to that routine. So if we didn't find the name of the table, return 0 and Y, return T name. So it's a name, right? We didn't find it's not a keyword, it's a name. And then if we did find it, that's here. Y is going to come from the keyval type table, and A is from the keytoke table. And if we go back now and look at AS1, where we're going to look for where we use the get is keyword subroutine. We see what we're doing is we're saying we call get is keyword, we store Y in the toke val, and if Y is not equal to 0, we say, okay, we're done. If it is equal to 0, we're saying it's a symbol. That's not what we want to do, because it's possible for Y to be 0 even though it's a keyword if it's a pseudo-op. So instead of comparing y to 0, we should just compare a to tname. Okay, if a is not tname, then we'll go down here and we're done. Otherwise, we go ahead and load oh, I see. This puts 0200 into Tocqueville, then calls lookup, which replaces. So actually, we don't need these. That was part of our debugging code before. So if it's not a name, then we'll go down here. If it is a name, we'll look it up, which will produce a symbol table entry for it, whether it's a previously allocated one or a newly allocated one. Put the address in tval, and we can just return tname. So we're good there. All right, so if we assemble now, we should see that instead of those .bss and .text being treated as symbols, they should be treated as keywords. And let's go to the front, and there they are. For example, there's right there. This was .bss, now it is a 9.4, which is a keyword. It's exactly what we thought it should be, something +4. Okay, and here's another one here. This was probably .data, right? Okay, good. So looks like the pseudo ops are now being handled correctly. I mean, they were actually already being handled correctly, but the code that's printing out the debugging code that's printing this stuff out wasn't. Well, okay, I guess they weren't being handled 100% correctly. Is keyword was working fine, but the getName function, the getName subroutine was not recognizing that these things were not being returned as names. All right, so now we have the issue that the dot symbol is actually a special symbol and should not really be returned as a symbol because it's a built-in symbol in the assembler, which means the current location in the assembly. And so I think it seems to me that the easiest thing to do would be just to add it in here. That makes sense to me. We just have to make sure we do it correctly. So we have e keywords and keywords and e keywords. That tells us how many of these things there are. All right, well, I think the code is written correctly. And assuming it is, we should be able to simply add another thing here, right? Yeah, I'm not going to go through and renumber all of these things. That would be silly, but I should be able to put here, like, I don't know, just keyword dot, for example. And then okay. Actually, yeah. Actually, this is wrong, but we actually have both dot and double dot. So let me call it KeyWDT. This label here is, just a throwaway label. We just need it for a second just to fill in the entry in the table. So this one will be dot, dot, dot. And this one is just dot. So we're adding both of these into the table. Okay. And then we're going to need this here. So keyword dot and, sorry, not HW, KeyWDT and KWDD. All right, and unfortunately if it matters, my table is not going to look so beautiful. It's not, now it has a line that's only too long. No big deal. I have to do the same thing here. All right, and this is going to be T dot and T, maybe D dot. Okay. The double dot symbol is not really used very much. It's only for very special cases, but nonetheless it exists. And so then we'll add this here. And actually, because these are just going to be zeros here, I don't have to worry too much about that. I'll just put it in here with zeros. Like that. Okay. And let me just put those in there and get rid of them there. There. So basically 12, 13, 14 zeros there, and I have 8, 9, 10, 11, 12, 13, 14. That looks good. Okay, so my tables here don't look as beautiful as they used to, but everything should be fine. And the only thing we need now is to define these tokens, T dot and TDD dot, the dot and the double dot. Yeah, I'll just leave it like that. Okay, so let's save that. Load AS1, AS0, which is where these tokens are defined. And let me just look at TPSE. There it is. Okay. Where do I want to put these? I suppose it's safe enough to put them here. I'll make that one C0. Yeah. Well, it doesn't really matter. I'll make this one TD dot, okay? Okay, so now when I save a symbol, I should see that those dots are not printed as dots, they're printed as C0, as token C0. And they are. Here we go. See? C0, C0. And this malloc is for this one here, for this symbol in error. And this malloc is for the symbol toke file, and this malloc is for the symbol lines. All right, and this symbol is malloc is for IO error, for hex error. Malloc is for CHR error. Then there's no malloc for this one because if you remember, it has the same hash value as hex error. So it's going into the same block of memory that was allocated at this point. All right, malloc, malloc, malloc. getC doesn't have a malloc. It's probably hashing to something that, one of these is hashing to. There's a malloc for peekC, but then every time it's used after that, there's no new mallocs. That all looks good. All right, so, it looks reasonable. I wouldn't say that there's nothing obviously wrong. So I think what I want to do now is write some code that will dump the entire symbol table in a very wordy and space wasting way so that I can get a really good look at what's going on in the symbol table. And that's not a problem. It will dump it out and it will be go to the printer, and then I can pull up my emulated printer and see what the symbol table looks like at every point after a symbol is implemented. So I'm going to write the code that will dump the entire symbol table, and then after every symbol is added to the table, I will dump the entire table and see what it looks like. And that should let me know for sure if everything is happening exactly as it is supposed to. And if it is all happening exactly as it is supposed to, then the scanner will basically be finished, and it will be time to start working on the parser. And that's very exciting because when the parser is, let's put it this way, the parser can be done in a simple, basic way that will allow us to have the assembler assemble itself. And then once it's assembling itself, it can be expanded and have all the features that we want to have. So that means that once we're starting the parser, we're very close to having a self-hosting assembler, which is the very first goal we have. I would dearly love to stop using this Orca assembler. Not because it's terrible, but just because I want to get off of it and use my own assembler to assemble itself. So let's work on writing that code to check the symbol table. So we'll put it in this file. And this is just debug code that later will be deleted because it's not necessarily long term. It's not necessarily long term. But it will be useful in the short term. So I'll just call it dump. And yeah, I'm not really sure it has to be entry or not, but who cares? It doesn't matter. Okay, so what I'm going to do is I'm going to go through and print. Remember the symbol table. Let me pull that diagram up again. The symbol table has 64 pointers for the different hash buckets. And what I'm going to do is just go through and print. If the pointer here is null, I'm going to print null. If there is a pointer, I'm going to print the address that it points to, and I'm going to then follow this chain and print all of these blocks out completely. And so it's going to take up a lot of space because it's going to print. Every time we dump the symbol table, it will print, probably at least 100 lines of output, but that's okay. My emulated printer has a lot of paper, and so I'll be able to see exactly what's going on in the symbol table. All right, so I might need oh, that's a mistake. I don't want that. We had that issue last time. All right, anyway, so I probably need a variable here. And I'll just call it ix. Okay. Well, let's just start this. We're going to go, the whole plan is to go through this list of all the entries in the symbol table. So get the high byte of the entry in the symbol table. If it is not null, we'll go down here. If it is null, right, I'm going to just print the word null, but I'm thinking what I probably want to do is, okay. Okay, symbol table. And so on entry here, I will just print that out, print out the string symbol table. Okay. And then we have here, I'm gonna just change it to 1 because I suspect I'll be coming back up here somewhere. Okay, so I think I'll do this. Actually, I'll do it like this. I know, I'll do it like this. Say LSR-A. So this is going to be the offset in the symbol table. So it's going to start with 0 and then be incremented by 2. I'm going to divide by 2 and print out that divided by 2 as the entry. So this will be entry 0, then entry 1, entry 2, entry 3, as X will contain offset 0, offset 2, offset 4, and so on. So let's go ahead and JSR to put XB. I don't have a routine to print out decimal numbers right now, so we'll be satisfied with hexadecimal numbers. And then we'll print out a nice little colon. All right, put that. Okay, and I have this thing down here, IX. Actually, I can load A0, store A and IX, put that there. Then this is probably going to be the top of my loop. Load X, IX. Okay. Now I'm going to have to load it again here. That's fine. Actually, in this case, I don't even have to. I can just load A and then there. That's just for printing purposes, to print it out. All right, now load into X. Get the high byte of that entry in the symbol table. If it's not equal to 0, go down here to dump 1. If it is equal to 0, then I just want to print out null. JSR puts. And we'll just include a new line in that string. Okay. So it'll print out the string null because it's null. And then we just increment X. Well, actually, we increment this variable IX twice. And we can then load it in and see if it's 64. If it's not 64, go to dump 0. All right, so we initialize IX with 0, load it in, print it out. Well, divide by 2 and print it out. That's the entry number, put a colon, and then get the pointer from that entry in the symbol table. If it is not null, we go down there and do something else. If it is null, we print out the string null. We increment the offset by 2 and check to make sure if it's 64. If it's not 64 yet, we go back to dump 0 because we have more things to print out. So that's all fine. Now at dump 1, we're going to say what happens if this thing here, this pointer, is not 0. For example, here, we have to print all this stuff out. All right, so what we're going to do here now is we're going to go ahead and print out the address of that pointer. It's not null. We got it here. It's not equal, so we go down here, and this is the high byte of the address. So we can just go ahead and print that out. All right, and then we can load the low byte of the address and print that out. All right, and to be honest, I don't recall if calling put xb destroys x, but we'll just assume it does. So if it destroys x, we're just getting x back here, and then getting the low byte and printing that out. All right, now that we've printed out the address, what we've printed out is the address of this first block here. We need to print out this first block here. And it will probably be easiest to do that using a zero page pointer as we did before. What I'll do here is, I guess, yeah, I'll go ahead and grab the zero page stuff here. Okay, so push the old contents of the addresses we want to use. Okay. Oh, and by the way, here is where this is where we go if we're at the end. Okay, print the string, and let's just call this dump 9 because we'll probably come back up here from somewhere else. And here is where we're going to end. So we will, restore these zero page locations. So 50 and 51 and return. Okay, so when we enter, we push 51, push 50, and when we exit, we pull 50 and pull 51 to restore them. All right, so now we have these zero page locations available to us. All right, and we've printed out the pointer, and let's just store this pointer in the zero page locations. So store A, this is the high byte there. Okay, and we'll store that the low byte there and print it. And now we will just jump to D block, which is dump block. I mean, what I mean by block is one of these things here. All right, and after we do that, I think we can just go directly to dump 9. So we're dumping, what D block will do, actually, maybe D block is not the right name for it. We need a routine that's just going to dump this entire chain. Yeah, no matter how many things are in it. So let's just call it dlist. It's going to dump that list, and then after it dumps the list, we go up here to increment to the next location in the symbol table, and so on and so on. All right, so now we have to write dlist. Okay, and we enter this having the pointer to this thing in our zero page location. Okay, so what we'll do here is, I think what we'll do here for dlist is we'll just JSR to dblock, which will print out one thing, one block. Okay, and then let's think a little about how dblock's going to work. It's going to print this out. I think what we'll do is we'll make sure we don't touch the pointer in locations 50 and 51. Don't touch that. So that means here all we have to do is go ahead and get a 30 in Y, because this is offset 30 from the beginning. All right, and we're going to then load. Okay, we're getting our, that's going to give us, actually we should get 31, not 30. We should get this one first, get the high byte first. All right. And if this is null, then we can go down there somewhere. Okay. If it's not null, then we're going to want to print it out. But maybe first we'll just move that. Can we push it? And decrement Y to get the low byte of this link pointer. And no, I guess we don't have to do that. Let's just go ahead and print it out. Okay, so if it's not null, then we'll just JSR put XP, print that one out. Okay, we don't know how that affects the registers, so we're going to have to reload Y with 30, and then get the low byte and jump, put XP. Okay, so what we're doing is we're printing out the address of this, the address stored in this link field here. That is to say, we're printing out the address of the next thing in the chain. Okay, and once we've done that, we actually want to get that same address and store it into our zero page locations, and then print out the next block and so on. But before I do that, let's think about the case of this is a null pointer. If it's a null pointer, then we can print our null string again. And I suppose we can return, because we've printed the entire list at that point, right? Yeah, I think that makes sense. Okay, when we print the block, we're going to print these two things. And I think we would maybe like to have here, whoops, link. Okay, a string link. So after we print out the two entries in the block, we're going to get we're going to print this out, this string here. And then after that will come either the address or the word null. Okay, after we print this out, we're going to have to print a new line as well. We're printing out the address. So the null has a new line after it, right there, the 0A. We'll print a new line there after we print out a non-null address. Okay, and also I'm going to have this be indented a couple of spaces. And then at this point, we need to go ahead and get these same bytes that we just printed out and put them I'll just do it like this. Just go ahead and get them again like this. And I guess put that in X, decrement Y, put that in 50, put X in 51. All right, and then jump to the top. All right, so we've got a non-null link here. So we print out the address that's in this link, and then we take the address and store it in our 0 page locations, and then we just jump back up here and print the next block out. All right, that looks acceptable to me. Now we have to print the block. All right, and also coming in here, when we enter this subroutine, we have a pointer to the block and locations 50 and 51. So we are going to start with loading a 0 into Y. And check the first byte of this here. Now, if we have a block, this thing had darn well better be filled, because that's the way it's supposed to work. You would not allocate a block unless you have a symbol to put in there. So if you allocate a 32 byte block, this one at least should have a symbol in it. This one may not, just like here. This one has a symbol, this one does not. That's okay, but this one had better have a symbol. But nonetheless, we're not going to assume that for the sake of our printing out our debugging code that prints out stuff, because if it doesn't, we want to see that it's screwed up. So we will, if this is 0, well, if it's not 0, we can just go down to dblock 1. If it is 0, then we need to print out something that says, hey, this is a problem. All right, and I think what I'll do is something like this. Okay, this is telling me that there's an empty space there. All right, so that would be this case here. So load X, if it's 0, print that out. And just go down somewhere else. Then this is the case where it's not empty. And for this, what we need to do is we're just going to use the puts routine to print out the name of the sample. But first I would like to, let's print out a little left bracket. All right, and now I will go ahead and load. Right, I can't assume that y is still okay. All right. Oh, no, that's not right. The symbol is at the address. I just need to do this. That is, get the pointer to the symbol in X and Y, and the pointer of the symbol is in these two 0-page locations. And JSR puts. I think I said in the last episode that kind of in general, we can't use puts to print these things out because puts relies on the string being null terminated, but these symbols are not necessarily null terminated. You could have a 12-byte long symbol, 12 characters long, that fills this entire space, and then after it comes the type, which doesn't have to be 0. But for now, the type is 0. So for now, this will be just fine. If we have a symbol that's really long, which we won't, at least right now. But if we did, this type would still be 0. And so the puts would work correctly. Okay, so put C. Okay, so that prints out that symbol. And now we basically want to do all the same thing over again. And if this weren't just debugging code, I might want to do something to loop back up and do this again. But for the moment, this is just debugging code. I don't really care that much. I'm just going to go ahead and sort of repeat the code for the second element here, right? So I'll put 15 into Y because the offset in the block of this beginning of this part here is 15. Okay. And if it's not equal to 0, then go to D block 3. Why not? All right. I'm just copying the code. And after I'm done with this, I'll jump to D block 4, which will just be exit. Okay, D block 3 is going to be just a copy of that code up there. Okay, and here is D block 4, which is just going to be to return. Yeah, I believe that's correct. After we print out this thing, we actually need to print out a new line here also. With this one, we already have the new line incorporated in that. Okay, but after this one, we need to print a new line. And here also we'll have to print a new line. Okay. And so now we need, whoops. We need to get the whatever's in 1551 plus 15. So add 15 and then put that in X. All right, 51, add 0 for the 16-bit add and put that in Y. And JSR to puts. All right, that looks good. At least I think so. It looks good, right? Is it good? I don't know. But all right. And so to test it out, what I will do, and I'm glad I made it an entry point here. To test it out is what I will do first. That's a good point. Do I want to try the whole thing all at once? Yeah, I can just go whole hog. Let's save that. And go here to AS0. And find where I call PRToke. All right, this is where I close it. So what I'll do is just right here, I will JSR dump and see what happens. I didn't see any errors there in the assembly. Aha. So here's the previous stuff we had that prints the tokens. Here's our symbol table. Okay, so we have all these are null. Okay, then we have, okay, I really want a new line there, but it's otherwise not so terrible. Toke tab and empty, the link is null. Link null, pixie, and fatal are both in the same thing. FD and then empty, hexair and CCair. Okay, so yeah, I'm going to just go ahead and put this new line right there. Just to make it a little bit easier for myself. And that would be here. Here's where we print that thing out. Okay, well, there's a new line there. Jump delist. Oh, it's just this first time we do it right here. That's where it is. It's when we call delist. I see. Put XB. Right. So here it is. There. Put the new line there. Okay, good. All right. Okay. Give us our symbol table. All right. No, 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 no. Okay. I mean, this is really just a matter of presentation. But it helps me to see it. Okay, LB stir. Okay, that one there. Okay, and right down here, let's just do this. Okay, let's put a new line before we, so it's a new line, symbol table, new line. Okay. So here's the symbol table. No, 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 no. And then this one has toke tab and then an empty space, link null. That looks great. Okay. chur error, empty space, link null. Pixie and fatal both map into entry 9, both hash into 9, link null. Okay, 10, FD, empty, link null, then null, 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 null. Hexar and CCR go here. Okay. By the way, I'm just curious about getC. Because I'm just thinking about getC. Remember up here, I never saw malloc printed out for that, for this getC. Well, we'll find it in here somewhere probably. I'm not seeing it at the moment, but anyway, let's keep going. See if you have it. Okay. Okay. Now toke file empty, get C0 empty, nbuff get C1, get C2 empty, get C3 empty, get C4 empty, error empty, null, lines empty. I mean, it looks actually quite good so far. The only thing is I was hoping we would see, like, there's no hash buckets that have more than 2 symbols in them, which is actually great from a hashing point of view. But just to make sure things worked, I would like to see actually an example of something with more, a hash bucket that has more than 2 symbols in it. And also, where is that getC? This symbol right here, getC. Why is that not in the symbol table? That's kind of bugging me because we never saw a malloc for it. So I assumed it was being put in with something else. There's the malloc for getC0. Let's see. And I see getC1 was in the symbol table, right? getC0, getC1, right? getC2, getC3, getC4. Those are all in the symbol table. Where do those come up? There's the malloc for getC4. And there's a malloc for getC0. There's the malloc for getC2. And a malloc for getC3. Those are all indeed the first thing, the first symbol in their bucket, right? Yeah, getC0. No, getC1 is not the first symbol in the bucket. getC2 is. getC3 is. getC4 is. So there should be no malloc for getC1. It was the same thing was malloc for nbuff. That, I think, is right. There's a malloc for nbuff right there. And getC1, we see that here. Here's where it's used the first time. There's no malloc. Here's where it's actually defined. There's no malloc. Okay, that all looks good. So far, I'm pretty happy with stuff. In error toke file lines. I have all this stuff. But the one thing I just don't see there is this getC. That is indeed a symbol. It's being printed as a symbol. And yet there's no malloc for it. But I don't see it in the symbol table. Well, I guess the only thing that we have to do is we have to go in and just dump everything. So what we'll do is go down here maybe we don't want to do it here. We'll go back here. And that's not the right thing to do. Let's look. We're going to look for lookup. Okay. After every time we look up, it puts the pointed symbol table in Tocqueville, which is not going to get messed with. So we're free to JSR dump. All right, and for good measure, we'll put another new line after that. So we should have lots and lots of symbol table dumps, all going to our emulated printer, which has an infinite supply of paper. All right, let's go up more. Okay, we've just put in error. We see that. And here's Tocqueville, so we just put in Tocqueville. And here's lines, we put in lines. Okay, and for IO error, we put that in. Where does IO error go? Okay, malloc 3240. Tocqueville in error lines. Tocqueville in error lines. Empty, empty, empty. Oh, I see. We're not printing the entire symbol table. This is only half of it, right? It's only from 0 to 1F. But we need to be printing from 0 to 3F. So that's probably what's going on, which if so is fine. It means that the symbol table code probably is working right. It's just that we're not printing the whole symbol table out. All right, and let's see what's going on there. Oh, I see. Yes, this is the offset, not the IX is the offset, not the entry number. So it needs to be compared to 128, not 64. All right. Okay. And probably we'll see now that everything's just fine. That just what was going on is that we weren't printing the entire symbol table. Yeah, look at all that empty space down there. Okay, lines. And now it's IO error. Yeah, and it got put there at 2.2, which is after 1F. And I assume we'll find get C is the same way, that one that I was worried about. Hex error is put up there. I'm just going to go find that thing. To tab, ISC tab. Here it is, get C. And where was get C entered? Aha, it's right there in the same bucket with stir error. Right there. So it is there. We just weren't printing out the whole table. Let's go down here and look at the final printout, which is all of the symbols, the whole table, all of the symbols. Okay, okay. Okay, so the only real issue I have here now is that we have no bucket that has more than 2 symbols. And yet I want that, because if I don't have that, I'm not really testing very well. I'm missing the whole possibility that that there's more than two, that has to allocate, basically it has to create this next block on the chain. That's not being tested at all. So let me save that and just load my test file. And actually, you know what I ought to do? I ought to load this and just try dumping all of these symbols in it. All of these right here. Okay, so let's use the lame copy and paste. Don't delete the lines. No, don't want that. Load test. All right. And I'll just put them right up here. Okay. Now I'm going to, oops, I didn't really mean to do that. All right, turn off insert mode. Yeah, I'm not really super thrilled with this editor, but I mean, it works. So that's a future project. Write an editor. Yeah. If I were to write an editor, I would probably write a little VI clone. And I know that there are already VI clones available for the Apple II. I mean, not for the Apple II, for 6502 processors, probably including the Apple II. But I would write my own just because, right, that's the fun part. Using someone else's is not as fun. So, but that's not the current project. The current project is the assembler. So that looks good. Now let's see if we can get some more collisions with all of those symbols. I almost thought there was a problem there. Okay. Here we go, symbol table. Okay. Aha, here's one. Into hash bucket 15, we got TSTY in buff, and then a link to the next block, which then contains get C1 and empty. Okay, that looks nice. Here's another one, right? TBCC, TADC, and then a link to the next block, which contains read. Another one, bucket 34, well, hex 34, tbit, tbreak, and then a link to the next block, which has stab and empty. Here, TOS, TLSH, a link to tjump and tdot. So there we go, 4 in that bucket, and 4 in this bucket. Okay, that's not so bad. Right, now the way hashing works, of course, is we would really love to distribute the keys, that is all these symbols, evenly across all of the hash buckets. And so it's not ideal to have some here with null, that is nothing's hashed to entry 1, right? Or nothing's hashed to entries 11, 12, and 13 here. Nothing's hashed to entry 18 here. And at the same time, we have, 4 things which all hash to this entry here, entry hex 3C. But my hash function is extremely simple, and I don't feel that this is a big problem. I think for the time being, at least, it's fine. And it's like later, if we find, oh, it's just too slow, then we'll have to go back and revisit this. There's also the possibility of having when you know how big your code is going to be, which we don't really know right now, you could say, oh, well, I have 39 kilobytes available and my code is 16 kilobytes, so I'll just allocate a gigantic, gigantic. I'll just go and allocate an 18 or 19 or whatever, a 20 kilobyte hash table, and won't bother with all this, chaining of linked lists and blah, blah, blah. Yeah, it's definitely a possibility. But I think I like this idea of building these chains off the hash bucket because it allows our hash table to fill up all available memory without running out of symbol table space as long as we have memory left. And that's kind of nice. So I'm going to say it looks like everything is working just as it is supposed to. So the next time we will start working on parsing statements. And the big topic in parsing statements is expressions, because parsing expressions will allow us to do all sorts of arithmetic. But I'm not going to do the full expression parser right away. I'm going to do something pretty simple and limited just so that we can switch over to using my own assembler to assemble itself as soon as possible. And then once we've done that, I'll build the full expression parser. So it's going to be parsing expressions and recognizing all of those instructions and generating the object code for them. And once we have done that, which I'm just going to go out on a limb here and say it's going to take maybe 4 or 5 episodes, we'll have an assembler which can assemble itself. Even though it's by no means finished, it will be able to assemble itself, and from then on we can use the assembler that we're writing to assemble itself and continue development until all of the features have been implemented that I want to have. So until next time, I will see you later.